Welcome! In this session, we'll explore a classic string manipulation problem, finding the maximum number of words in a list of sentences. We'll break down the problem, analyze different approaches, and discuss the most efficient solution. Let's dive in. In this problem, you are given a list of strings called sentences, where each element in the list represents a single sentence. Your task is to determine the maximum number of words that appear in any one of these sentences. Now, what exactly do we mean by a word? A word is simply a sequence of characters that are not spaces, and words within a sentence are separated by single spaces. The goal is to return an integer that represents the highest number of words found in any single sentence from the provided list. For example, if the input list contains 3 sentences, you would check how many words each sentence has and return the maximum count among them. Let's look at the first example to understand this better. The input consists of 3 sentences: Alice and Bob love LeetCode, I think so too, and this is great. For the first sentence, we can count that it contains 5 words. The second sentence has 4 words, and the third sentence has 3 words. Out of these, the largest word count is 5, so the output for this example would be 5. Similarly, in the second example, we have 3 sentences: please wait, continue to fight, and continue to win. The first sentence has 2 words, while the second and third sentences each have 3 words. The highest count here is 3, so the output in this case is 3. Now consider the third example, where the input list contains only one sentence, hello. This sentence has just a single word, so the maximum number of words in any sentence here is 1, which is also the output. From these examples, you can see that the solution involves counting the words in each sentence and then determining the largest count among them. It's straightforward once you understand how to count words and compare the counts across the sentences. Finally, let's go over some constraints and edge cases for this problem. First, the input list will always contain between 1 and 100 sentences, so there will always be at least one sentence to process. Each sentence will have a length between 1 and 100 characters, and sentences consist only of English letters, spaces, and no leading or trailing spaces. Words in a sentence are separated by single spaces, making word counting consistent. Edge cases might include sentences with only one word, such as hello, or lists where all sentences have the same number of words. You might also encounter sentences of varying lengths, like short verses, this is much longer. Ensuring that your solution handles all these cases will guarantee its correctness. To solve this problem, we start by considering 2 main approaches. The first is the brute force approach, which is very intuitive. Here, we process each sentence in the input list one by one. For each sentence, we split it into words using Python's split method, which generates a list of words. The length of this list gives us the word count for that sentence. As we iterate through all sentences, we keep track of the highest word count encountered so far. This method is straightforward and easy to implement, with a time complexity of O(n), where n is the total number of words across all sentences. Since we only store a running maximum, it uses O(1) additional space. However, a trade-off of this method is that splitting sentences into intermediate lists introduces some overhead, which is unnecessary if we're only interested in the word count. To address this, we also consider an optimized approach. Instead of splitting sentences into lists, we can count the spaces directly within a sentence. Each space represents a separation between words, so the total word count is simply the number of spaces plus 1. This avoids the overhead of creating temporary lists and is a more efficient way to process the input. Now, let's break down the optimized approach step by step. First, we iterate through each sentence in the input list. For each sentence, we count the number of spaces using the count method in Python. Adding 1 to this count gives us the total number of words in the sentence, because spaces separate words. As we process each sentence, we keep track of the maximum word count encountered so far. This approach runs in O(n) time, where n is the total number of characters across all sentences, since counting spaces in a string is a linear operation. It also requires O(1) additional space, as no extra data structures are used. A key advantage of this method is its slight performance improvement over the brute force approach, as it avoids creating intermediate lists entirely. This makes it well suited for memory-constrained environments or scenarios where efficiency is critical. Additionally, we briefly consider another alternative, pre-processing. In this strategy, we compute the word count for all sentences upfront and store them in a separate list. This allows for efficient repeated queries, but it introduces extra memory usage and is unnecessary for our current problem, as we only need the maximum word count once. Now let's analyze the pre-processing alternative further. While its time complexity remains O, n, since we still process each sentence once, the space complexity increases to O, m, where m is the number of sentences. This is because we store the word count for each sentence in a separate list. This trade-off can be worthwhile if the word counts are needed multiple times, such as in scenarios with repeated queries or additional computations. However, for our problem, this approach introduces unnecessary memory overhead, as we only need the maximum word count and do not require word counts for individual sentences afterward. Given these considerations, we chose the optimized approach as our final strategy. Counting spaces directly in each sentence and adding one to derive the word count is both efficient and simple. It eliminates the overhead of creating intermediate lists, ensuring faster execution. Moreover, it's easy to implement and scales well with input size, making it suitable for large datasets. Finally, let's summarize why the optimized approach is preferred over the alternatives. The brute force approach, while simple, incurs extra overhead due to the creation of intermediate lists for each sentence. On the other hand, the pre-processing approach introduces additional memory usage to store word counts, which is unnecessary for this problem since we only need the maximum count once. By counting spaces directly, the optimized approach strikes the right balance between simplicity, efficiency, and memory usage. It achieves the goal with minimal computational overhead and no additional storage requirements. In our final solution, we count spaces in each sentence, add one to compute the word count, and track the maximum value across all sentences. This approach is concise, efficient, and well-suited for the constraints of the problem. In this problem, our goal is to determine the maximum number of words found in any single sentence from a given list of sentences. Sentences are defined as strings where words are separated by spaces, and each word is simply a sequence of non-space characters. To solve this, we'll break the problem into clear steps. First, we need to parse the input, which is a list of sentences. Our output will be a single integer representing the maximum word count across all sentences. The reasoning here is straightforward. We'll iterate through each sentence, analyze its structure, and count the words. Since words are separated by spaces, splitting the sentence at these spaces is an effective approach to extract the words and count them accurately. Now, let's split each sentence into its individual words. For this, we can use the split function, which divides a sentence into its component words by treating spaces as the delimiter. What's great about split is that it handles consecutive spaces seamlessly, treating them as a single separator. This ensures we get an accurate count of words even if the sentence has irregular spacing. For example, if the input sentence is "the quick brown fox," the split function will break it into a list of words, "the quick brown fox." Once we have this list, the next step is to count the number of elements in it, which tells us the number of words in that sentence. Using a function like len makes this straightforward. In our example, the word list has 4 elements, so the word count for this sentence is 4. To track the maximum word count across all sentences, we initialize a variable called max_count and set it to 0. This variable will store the largest word count we encounter as we process each sentence. For every sentence, we calculate its word count and compare it to the current value of max_count. If the current sentence has more words, we update max_count to this new value. Otherwise, we leave it unchanged. For instance, if we have sentences like "the quick brown fox jumps over" and "the lazy dog," the word counts are 4, 2, and 3, respectively. As we iterate through these sentences, max_count progresses from 0 to 4, and then stays at 4 for the remaining sentences. Once we've processed all sentences, max_count will hold the maximum word count, which is the result we return. There are a few key insights that make this algorithm efficient. First, using the split function is not only simple but also handles edge cases like irregular spacing automatically. For example, if there are multiple spaces between words or even empty sentences, split adjusts accordingly. Second, maintaining a running maximum with max_count ensures that we only need to traverse the list of sentences once, achieving an O(n) time complexity. Third, edge cases are handled naturally. Empty sentences return a word count of 0, consecutive spaces between words are ignored, and single-word sentences are counted correctly. As for data structures, we're primarily working with a list to hold the input sentences and a single integer variable, max_count, to track the maximum word count. The key operations in this algorithm are straightforward yet effective. First, we use split to divide sentences into words, which avoids the need for manual parsing and handles irregularities in spacing. Second, we use len on the resulting list of words to count them accurately. Finally, we compare the word count of each sentence to max_count, updating it as needed to keep track of the largest count encountered. In terms of complexity, the time complexity of splitting a single sentence is O(k), where k is the length of the sentence. Since we process all n sentences, the total time complexity is O(n*k), where k is the average length of a sentence. As for space complexity, the only extra space used is for the temporary lists created by split, making it O(k) for the largest sentence. Let's walk through an example to see how the algorithm works in practice. Suppose our input is the list of sentences, the quick brown fox jumps over the lazy dog. Starting with the first sentence, the quick brown fox, we split it into the quick brown fox, count the words to get 4, and update max_count to 4. Next, we process the second sentence, jumps over, splitting it into jumps over and counting 2 words. Since 2 is less than the current max_count of 4, we leave max_count unchanged. Finally, we process the third sentence, the lazy dog, split it into the lazy dog, and count 3 words. Again, max_count remains 4 because 3 is not greater than 4. After processing all sentences, the maximum word count is 4. After completing all the steps, the final output of the algorithm is the maximum word count, which in this example is 4. This means the sentence with the most words in the input list contains 4 words. By following this approach, we efficiently determine the result while handling all edge cases and maintaining optimal complexity. This code solves LeetCode problem number 2114, maximum number of words found in sentences. The objective is to determine the maximum number of words in any sentence from a given list of sentences. We start by defining the most words found method, which takes a list of sentences as input. Inside the method, we initialize a variable max_words to 0. This variable will keep track of the maximum number of words encountered so far. Next, we iterate through each sentence in the input list using a for loop. For each sentence, we use the split method to split the sentence into words based on spaces. The len function is then used to count the number of words in the resulting list. This count is stored in the variable word_count. We then compare word_count with max_words. If word_count is greater than max_words, we update max_words to the value of word_count. This ensures that max_words always holds the largest word count encountered during the iteration. Finally, after iterating through all the sentences, we return the value of max_words. This value represents the maximum number of words found in any sentence from the input list. The algorithm is efficient with a time complexity of O(n*m), where n is the number of sentences and m is the average number of words per sentence. This is because we process each sentence individually, and splitting a sentence into words takes time proportional to its length. The space complexity is O(1), as we only use a fixed amount of extra space for the max_words variable. This is the Java implementation of LeetCode problem number 2114, maximum number of words found in sentences. The code mirrors the logic from the Python solution, where we iterate through each sentence, split it into words using the split method, and calculate the length of the resulting array to get the word count. The maxWords variable tracks the highest word count observed across all sentences. Key differences in Java include explicit type declarations and the use of arrays for string manipulation. In this example, we start off with a simple input consisting of 2 sentences, "I love programming" and "Python is great." To find the maximum number of words in any sentence, we first initialize a variable max_words to 0. This will help us keep track of the highest word count as we process each sentence. Now, for the first sentence, I love programming, we split it into words using the split method, which gives us the list, I love programming. The length of this list, calculated using len, is 3. Since 3 is greater than the current value of max_words, which is 0, we update max_words to 3. Next, we move on to the second sentence, Python is great. Again, we split it into words, resulting in the list, Python is great. The word count for Python is great is 3, which we calculate by determining the length of the list, Python is great. We then compare this word count of 3 with the current value of max_words, which is also 3. Since the word count is not greater than max_words, we do not update the variable. At this point, we have processed both sentences, and the maximum word count we observed is 3. Therefore, the final output for this example is max_words equals 3. Moving on to the second example, we have 3 sentences of varying lengths, ABC, the quick brown fox, and hello. As before, we start by initializing max_words to 0. For the first sentence, ABC, we split it into words, resulting in the list, A, B, C. The word count for ABC is 3, determined using len, A, B, C. Since 3 is greater than the initial value of max_words, which is 0, we update max_words to 3. Next, we process the second sentence, the quick brown fox, and split it into words, resulting in the quick brown fox. The word count here is 4, which is greater than the current value of max_words. As a result, we update max_words to 4. Finally, we process the third sentence, hello, which splits into hello. The word count for this sentence is 1. Since 1 is not greater than the current value of max_words, which is 4, we do not make any changes. At the end of this example, the maximum word count is 4, so the output is max_words equals 4. In the third example, we look at a mix of empty and short sentences. The input consists of 3 sentences, an empty string, word, and another example. As always, we begin by initializing max_words to 0. For the first sentence, which is an empty string, splitting it results in an empty list. The word count here is 0, so max_words remains 0. Next, we process the second sentence, word. Splitting this sentence gives us the list, word, and the word count is 1. Since this is greater than the current value of max_words, which is 0, we update max_words to 1. Finally, we move on to the third sentence, another example. The sentence another example splits into the list, another example, which has a word count of 2. This word count is greater than the current value of max_words, which is 1, so we update max_words to 2. At this point, we have processed all the sentences in this example. The maximum word count across the 3 sentences is 2, so we return max_words equals 2 as the final output. This example highlights how the solution handles cases with empty strings and sentences of varying lengths. In this section, we'll analyze the time complexity of the algorithm. The code processes a list of sentences to find the maximum number of words in any sentence. First, we iterate over all the sentences in the input list. If there are n sentences, this loop executes n times. Next, for each sentence, the split method is called to divide the sentence into words, using whitespace as the delimiter. The time it takes to split a sentence depends on its length, or the number of characters, which we'll call m. This operation, therefore, has a time complexity of O(m) for a single sentence. After splitting, the length of the resulting list is determined using the len function. Since the length is computed during the split operation, this step has a constant time complexity, O(1). Adding these together, the overall time complexity for processing a single sentence is O(m). When we sum this over all sentences, the total time complexity depends on the combined length of all sentences. This brings us to the overall time complexity, which is O, sum of the lengths of all sentences. Let's call the total number of characters across all sentences L. Since the algorithm processes each character exactly once during the split operation, the time complexity can be simplified to O(L). Now, let's analyze the space complexity. The input list of sentences resides in memory, but it doesn't require any additional space allocation. When we call the split method, a temporary list of words is created for each sentence. If there are W words in a sentence, and the average word length is K, the space required for this list is proportional to the length of the sentence, or OM. However, this temporary list is only used briefly to calculate the word count and is immediately discarded, so it doesn't contribute to the overall space usage. Lastly, the algorithm uses a single integer variable, max_words, to store the maximum word count, which uses constant space, O1. Putting this together, the overall space complexity of the algorithm is O1, since no additional memory is required beyond the input and a few temporary variables. Let's compare this to a brute force approach. In a less efficient method, we might iterate manually over each character in every sentence, counting spaces to identify word boundaries. Although this would also result in a time complexity of OL, since every character would still be processed, the implementation would be more cumbersome. By using Python's split method, we not only achieve the same optimal time complexity but also take advantage of pre-optimized internal operations, resulting in a cleaner and more efficient solution. This approach is both time and space optimal, processing each character exactly once and avoiding unnecessary auxiliary data structures. Now let's consider the best, average, and worst-case scenarios for this algorithm. In the best case, all sentences are extremely short. Even in this scenario, every sentence still needs to be processed, so the time complexity remains OL. In the average case, sentences have varying lengths, but the complexity still simplifies to OL, because it depends on the total number of characters. In the worst case, all sentences are extremely long, resulting in the maximum possible value 4L. However, since the algorithm processes each character exactly once, the time complexity remains OL. This consistency across all cases highlights the efficiency of the approach, as the time required depends solely on the total number of characters across all sentences, regardless of their individual lengths. When working on this problem, there are several common mistakes to watch out for. First, failing to account for edge cases like empty sentences or an empty list can lead to runtime errors. It's important to validate inputs and consider boundary conditions thoroughly. Next, incorrect splitting logic can be a pitfall. For instance, using the split method without specifying the delimiter or overlooking multiple spaces between words might lead to inaccurate word counts. Another issue is ignoring performance constraints. Brute force solutions that iterate over all sentences with nested operations, such as splitting each sentence, can become inefficient for large inputs, so time and space complexity need to be analyzed carefully. Additionally, punctuation handling can sometimes be required, depending on the variation of the problem. If punctuation should be ignored when counting words, ensure this is addressed in your solution. Lastly, not optimizing for early exits can waste computational resources. If you find a sentence with the maximum word count early, exiting the loop can save unnecessary calculations. Now, let's consider some insights that are particularly useful in interview settings. Recognizing patterns is key. Many problems involve processing strings or arrays, so identifying the correct way to parse and evaluate data, such as splitting sentences into words, is critical to solving them effectively. Another important aspect is identifying opportunities for optimization. After implementing a brute force solution, think about ways to improve efficiency, such as early stopping, caching results, or reducing redundant operations. It's also essential to handle edge cases explicitly. For example, test your solution against scenarios like empty sentences, sentences with only spaces, or very large inputs, and be prepared to discuss these during an interview. Lastly, pay close attention to the problem constraints. If the problem guarantees no empty sentences, for instance, you can skip certain checks, saving time and resources. Understanding these constraints helps you avoid unnecessary work and focus on what's truly required. This problem shares similarities with other string manipulation problems, so practicing related problems can help you build a strong foundation. Examples include LeetCode 434, which involves counting segments in a string, LeetCode 58, which focuses on finding the length of the last word, LeetCode 151, which requires reversing words in a string, and LeetCode 2042, where you check if numbers in a sentence are ascending. Each of these problems offers unique challenges but reinforces similar concepts. Now, when it comes to approaches, the brute force method is an intuitive starting point. You iterate through each sentence, split the words, and count them. However, this has a time complexity of n*m, where n is the number of sentences and m is the average length of each sentence, making it less suitable for large inputs. A more optimized approach involves counting spaces directly during traversal. This avoids creating intermediate word arrays, which reduces memory usage. For problems involving repeated queries, pre-processing sentences to store word counts in a separate array can offer faster performance at the cost of additional space usage. Finally, another approach worth considering is using regular expressions. Regex can handle more complex definitions of words, such as ignoring specific punctuation or special characters. This can be particularly useful for variations of this problem where such nuances are required. However, it's important to note that regular expressions may introduce additional overhead, both in terms of computational performance and debugging complexity. While regex can be powerful, it's often harder to read and maintain compared to simpler logic. Therefore, you should carefully evaluate whether the trade-offs align with the problem requirements and constraints before opting for this method. Great job! We've successfully tackled the problem of finding the maximum number of words in sentences. Remember to practice and apply these strategies to other string manipulation problems. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!